Welcome everybody. This will be the next part to the video series for Task 8 in the 2024 Codebreakers Challenge. The last video we had identified the AES methodology appeared to be implemented correctly at least. The looks like the key and the counter implementation were based off of our SHA-256 value, which came from our elliptical curve functions. We have a couple more functions to disassemble or to analyze, and then we'll have to go through and make sure that ECC is actually implemented correctly so we can identify any vulnerabilities within that. So without further ado, let's just hop straight into this first function. So this first function, let's actually look at the parameters first, takes the SHA-256 structure, which we've seen several other times, takes our HMAC data, which comes in from here, and the HMAC length. So let's set these parameters, HMAC data, HMAC length. It looks like we reinitialize our structure based on our HMAC data this time. We have two possibilities. If HMAC length is less than 0x41, which it should always be, because if we remember, it's going to be hard-coded. We have that in the decrypt question mark. Nope, in command func, command thread. We have this stir n copy or stir n length. So our max would be 0x40. If we send anything larger than that, it gets shrunk to 0x40. So we should always hit this top run. This bottom run doesn't even matter to us then. So it looks like we finalized based on our structure on this. We set LVAR2. Actually, it looks like our SHA-256 is updated based on whatever's in memory already. So if param, all of those are 0, else come in here. If HMAC length is less than 0x41, we hit this, but it's not actually SHA-256 in our HMAC. So we need to identify what's actually going to be in that stack. There's a good chance it might just be no bytes. It could be garbage from previous sessions. We'll need to identify that. Because that's 0x40. What is this one? It's finalizing it into that spot. It's interesting. This one looks to actually do our HMAC data, but since it's on this if else, we're never going to hit this one, so we don't have to worry about it. We should walk through that just to make sure maybe Ghidra is misidentifying this, because this seems like an interesting setup. Then we have one more function down here, param1 plus 0x70. If we remember, param1 is our AES structure. The AEX structure by default usually doesn't go that large. We can actually look at the one in memory that we have here. If we go into tiny AES, AES.h, the structure itself, not AES, SHA-256. I don't have any SHA-256 code on hand, so we can't look at that one right now. We'll have to come back and maybe look at that, see what's usually at 0x70. We have LVAR2, which happens to be HMAC data in this case, since we're going to be up here. And then HMAC length will be set to 40, or, yeah, should be 0x40. No, yeah, 0x40. So it's going to be, this one actually does appear to be using our HMAC data. Let's go into it, change this to HMAC, change this to HMAC length. This will be our SHA-256 struct still. It's going to be offset a little bit, but we'll just keep it. We'll do plus 0x70. So in here, we appear to be doing a for loop where we're XORing the structure by 0x36. And then we're XORing the structure at 0x70 plus 0x40 by 0x5c. So it looks like we're trying to initialize the data to some kind of interesting value. We're going to come down here, take the length minus 0x40, which in most cases should be 0. If our HMAC is 0x40 in length, we're just going to assume top case in the worst case. This one's going to be 0x80. If 0x40 is less than HMAC length, set this to 0. And then it's going to be setting values to 36, 5c, Then we also have a thunk call down here with the same values. So if we look at this, this is actually, it's going to be Zoring whatever's at HMAC plus the counter with 36 and then with 5C. And then it appears to be whatever's left. That's what this is doing. So like, let's say our characters are actually only, our HMAC is only 20 characters in length. The first 20 characters will be Zord, but then we're still left with empty space. It's going to put just straight set that to 0x3C. And also 5C. So that's an interesting setup. So this appears to be like Zoring remaining data. Or Zoring the structure of some sort. So it doesn't look like the SHA-256 structure is the normal SHA-256 structure, just based on how they're interacting with it. This function doesn't appear to be called anywhere else, so we're just going to call it HMAC SHA-Zor init. Next one, we have just the SHA-256 structure. It appears that we're now going to SHA-256 the instance at 0x70 plus 40, so whatever was Zored by 3C, I believe. We'll do SHA-256 plus 0x70 underscore Zor. In this one, we then pass in the structure again, end buffer. What's important to notice is that we never called finalize. So it's probably going to be a corrupted structure. End a buffer, which we assumed is going to be the out, what we're writing to at the end. And then socket buffer length. So if I come in here, looks like update, we're now going to update on end buffer, which end buffer was set to be whatever was CTR'd. So it looks like end buffer is already set a little bit based on buffer length. So now we're going to SHA-256 this AES encrypted or decrypted data. And then we have one more passing the structure. We're going to save it into local 28. We're going to do another, we're going to finalize it. We're going to save it into param1, which is the output. We're going to initialize it again, and this time SHA-256 based on what was in the 0xB0. 0xB0 is going to be 0x70 plus 0x40, which was set to our HMAC Zored by 5.9 or 5C, one of those two values. We're going to update again based on this original SHA-256, and then we're going to finalize param3 probably zeroes it out. I'm going to guess this is zeroing it out because we're not actually interacting with param1 anymore. This is going to be a very just guessy answer, just zeroize. That one doesn't really matter as much because all we cared about was the output, and it looks like var28 is then checked against our checksum in memory. Excuse me. So with that, it looks like a lot of shine. This would be SHA-256 AES decrypted data. And this should be the final SHA-256. So a lot of functions going on down here that appear to just be setting up the checksum. We know what the checksum is because it appears to be socket buffer. So that's the data we send in, and we have that from our packet capture. So we kind of know what the checksum is. We have what's getting sent into as the socket buffer, but we don't know what the private key is yet. And that's kind of about it. So at this point, we could go two paths. At some point, we're going to need to probably... do we need to write this up? Trying to think. It might be easier if we wrote this up in our own C function so we could do testing. But it's also already written up for us right here. So we really don't need to, as the only things that are usually passed in are the HMAC and the private key. Right now we're still missing the HMAC. We don't know what HMAC is. And based on this, it looks like HMAC is Zord, but not SHA-256. So there's a chance that if we can kind of reverse this SHA process, we might be able to figure out what the HMAC was. We know what the if we can figure out what's supposed to be returned here, we can figure out what the AES decryption is. And if we can figure out the AES decryption is, then all we would have left is to figure out the HMAC. And if we remember, HMAC is what we're trying to figure out for this challenge. So I think the first thing we'll do is try and identify what is going to be decrypted here. The way to figure out what's going to be decrypted here is we need to figure out what the key is. And the key is set by this ECC function. So it's time to dive into the ECC functions and see if this is implemented correctly. So the major aspects of ECC are all done down here within the ECC point multiply. Since we have a C library, we can start implementing this ourselves. I'm going to do vim ecc.c hashtag include. You know what? I actually won't do that. I'm just going to go into nano ECC and modify their ECC file and just add a main down here. Not the most technically correct way to do this, since there's no main already in this file, because there's going to be a lot of functionality that we don't really care about, but this will make it easier for us to just implement this in one go. We know we're using curve 32, so we could probably hard code that. I think that's set here. We want to use curve 256R. I think that should be good, because this is going to then define our ECC curve as 32 bits, and then should default to our functions. So if I gcc ecc.c, it does compile, so that's good. Vim ecc.c, come down to our main. Now we just need to set up some values in memory to do some testing. I'm going to delete all our breakpoints because I don't remember where they're set. I'm going to set a breakpoint right here. Yeah, I'm going to set a breakpoint right here because we know when we walked through it the first time, we knew what buff bag was, because that's just the buffer of our, where it's output at the end, I believe. Oh, it's the value passed in. So we could actually set this up to be realistic, since we know buff bag is going to be sent in from our data. And this should just be the first 32 bytes of the private key, or first 32 bytes of the packet. This should be the second 32 bytes of the packet. So this should be 64 bytes in total. Local 98 should be our, looks like it could be either, should be our private key or our private key plus n, should be this first one. The second one should be random or p, so whatever random bytes or the p curve. Looked like random bytes last time, which in ECC point multiplication is normal, I believe. I think this example, ECC point multiplication, where are you at? Multip. What's the function called? ECC point mult. Point. Why am I not seeing it? ECC. Should be around the midway point of the file, I think. Oh, right here. Oh, lowercase c's. The p initialized z, p scalar, p point, p result is what usually gets passed in. So that's where it's going to be stored. P point would probably be our, if I had to look or think, if I can, p point is probably our private key. P scalar is probably the random. And p initial z would be our static value or some curve. Is this function ever used anywhere? ECC point mult. Okay, public key, curve G, private key. So this is in make key. It's also called down in shared secret, so this is probably the implementation that's already actually happening, is that we have the left product, the public key, the private key, and random. So public key appears to be this guy, which is set to private plus n. Private key is, oh, there's a random here. So it does appear to be using random, so maybe the order of arguments is slightly off. So maybe buffer begin is probably our public key. This is our private key plus n, and then there's our random. So it does line up, it looks like. We just need to find a way to then call it. I'm just going to copy this function, mostly because I don't want to have to call that. At some point we'll be calling this, not that, this. So I think we should try and figure out what the normalized values of a lot of those are. Random is just going to be random bytes. The way elliptical curve cryptography works is that you should take a random curve and do some confusing math on it. We could do a refresher on elliptical curve cryptography, but I think I'm not the correct person to kind of give you that refresher. I'm here to give you the exploits. So do a quick, just like recap video. It's a lot of like, how does ECDSH work, or EDSA? ECDH. Elliptical curve Diffie-Hellman is what it appears to be. ECDH. So if you come into the elliptical curve Diffie-Hellman, you can kind of see that the shared secret is calculated based on D, your private key. We'll actually come into this because this right here, this page right here has everything we need to exploit. So I'm going to leave this one open, but it looks like your private key times Q, Q is your private key times G. So yeah, so it looks like Q is the private key. No, Q is the public key. So Q, Bob's public key times Alice's private key gives the same equation as Bob's private key times Alice's public key. And public key is just defined as your private key times G, which is the curve G. Then I think there's one more piece I wanted to identify. I think that's it for now. But the fact that we're just a random value means that you're on the curve, or n is the curve. The random value just identifies that you're able to identify points within the curve, and then the private key and public key would actually prove that you're on the correct curve for the product. Well, product's actually the result, so that doesn't matter. Yeah, I'm going to copy that because that's going to be our product. So how private or elliptical curve is kind of defined, or in value-wise. We identified that public key is 32 bytes, and the public key is 64, and the private key is 32 bytes. That's because the private key is actually just one point in this 2D array, so it's an x and y coordinate system. And that's just usually the x coordinate, whereas the public key is going to be x and y. We could kind of identify this as well with the G curve. Go to G underscore curve 32. This one was 64 characters in length, and we set it as a 2D array. The first curve, or first index, will be the x point, and then the second would be the y point. It doesn't really matter much besides the fact that there's 2 points with that. But yeah, I think that should be it. There's a good chance, since the bag buffer, remember, is 64 bytes, that's going to be the public key, so that lines up. Private key, and then random. So all we need to do is, I'm going to set it up so our public key is actually the correct public key in this instance. If you remember, the public key should just be the first 64 bytes sent in, since it just grabs our buffer, sends it straight in, and it's just 0 and then 24, or not 20, 0x20. So I'm going to set a char pointer p underscore public key. There's a chance that public key is actually supposed to be a specific type. Let me just make sure it's not. Curve G. That should just be an array, so this should be fine for me to just send in a character array. I'm going to do unsigned character, just to be safe. And not set that, I'm going to set this to 64 characters in length. We're going to need to open our data, which if we remember, we saved it back here, couple directories. We saved it under, I think, data. Am I just missing it, or did we not save it there? It's back another directory. There it is, data.raw. So go back 3 directories, data.raw. So I'm just going to do int file descriptor is equal to open. I'm just going to use regular open and not fopen. / data.raw. Open this as read only. Don't do character read only because this isn't fopen. You need to set this to 0. There's a chance that if you don't set to 0, it's going to be accidentally initialized to whatever's left in RSI, which could cause problems. I've had that happen before. So p_public key is now going to be read into from the file descriptor. We only want to read in 64 characters. We don't care about the rest of the buffer right now. We're just going to read in the first. Read that in. We can probably close FD right now. We don't care anything else about that. Private key, we're still not sure about. We could set that to a random value. Just have it be the same. Unsigned char as the remote instance. Unsigned char, we'll set this to p_private key. Set this to be 32 bytes. This one's not going to be 64. I'll just do memset p_private key. We can check to see what we call or set it as. Cat ecc_private key. We set to B's. We can set this to the letter B 32 times. Random, pretty much just random bytes, but we're going to want it to be, I think we want it to be the same. It shouldn't matter because ECC point multiply should always give you the same value back no matter what, even if the random is different. So I'm just going to set up a quick random value. We could just set it to an exact value as long as it's constant. I think that's constant should still work. Random 16. Heck, we could just set this all to zeros, and that might work. No, zeros will not work because it has to be a relatively prime to P, I think. Yeah. Zeros would not work. I think there might be a get random function in here. Because it's calling pre-random a lot. I would be surprised if there's not a way to generate a random number. P-random. Oh, that's mine. That's interesting. So it has the, maybe we need to go into apps, make keys, and see how it uses random. Oh, right here. Just get random bytes. Random file descriptor. So we could do it so it's set up to make sure that the random bytes that are grabbed are correctly prime with it, but I'm pretty sure there's a good chance that it's going to be that way no matter what. So let's come back to this file. We'll just open up urandom. Rand f file descriptor is equal to open at sysdev/urandom as read only. We're going to read 16 bytes from there. So rand fd into prandom. 16 of those, I think it's 16 bytes. We could check here, won't be a good example. Let's just go back into this one. Apps, make keys. It's going to read in get random bytes, number of ECC digits times the size of uint. So that should actually be 32. Because we are using curve 32. We can close that. Close random fd ECC point multiply. So we have private key, public key. The product is just where it's going to be stored. We could actually just print that out if I'm correct in my assumption. I think we can just do lproduct.x and it should be a character array as well. Yeah, lproduct.x. And that should be what's returned at the end in out of this function. It should just be an x coordinate because that's all it really cares about, or an x value. So we do for int x, which is equal to 0. X is less than 32 x plus plus. I think 32 should work. Printf %0 to x. Add a space because I don't want new lines, and we're going to do L underscore product at x at x. I'm going to run it once just to see if it runs. It didn't even compile. P underscore public key. Oh, I didn't define it. No, I did. P underscore public key. Oh, I did capital. Okay. That should be all good. I don't really care about the warnings too much. So we got an answer back. So on our using the raw data, this is what in theory should come back using the private key of all B's. We can test this out by where we at context. I think we just deleted all our breakpoints, so we can set a breakpoint at ECC multiply. I know I'll give you a hint and tell you that we're missing some stuff. Like it shouldn't work in my head. But I'm going to show why not first. Or I'm going to show an example of it not working first. So continue. If we come over to our version that we're sending data in, we should be able to just go back, netcat techu localhost 9000, and just send in data.raw. And that should be 101. That should be our out buffer, I think. Buff bag, so it's actually our buff bag, or our public key. This should be the public key that's sent in, so 96C298D8. It's also where it's going to be stored after, so I'm just going to copy this. Our public key should be, or private key should be this, but this should be plus, this value should be plus the curve n to minus 0x C2, not C2, 62, 62, 62, 62, or don't want to do dump, I just want to print. 512563FC sounds very similar to the n curve. 512563FC, yep. So this is our private key plus n. Context, let's see, we have private key. Our random shouldn't matter because that should just be a random value that we're creating. And then the size should be the last thing. So all we want to keep is this one. Do next instruction. Dump this out and see that we have 19B01E. Now I think these should be different. Let me come back to our example where we ran it. And they are in fact different. Now if everything lined up correctly, they should be the same. Even if we're using the incorrect private key, as long as the private keys are the same, we should still get the same answer. So that means something is wrong. So we need to actually identify what our private key and public keys are looking like. So I'm going to come in here and print out the first 32 bytes of our public key. Because if we remember, the private key and public key aren't being directly passed in. They're going through these copy functions, which we assumed were just copying the memory. We didn't really step through them too great to identify what they were doing. So we need to do that this time. Not that one. Where's the one I sent the data with? Is it this one? Send the data. We're going to compile this, don't care about printing the final one right now. Print this out. We have 6B171D ends with 96. But if we come look at what the private or public key is right now, it actually starts with the 96, C298. So it looks like it's our public key, but just reversed. So yeah, so everything's just reversed. We could probably confirm this with the Y coordinate as well. GCC. And it looks like 4F will be at the end of what we're expecting. So we just need to reverse those bytes in place. We can create a quick function. Void reverse for, we'll do char pointer A with size, int size. We should be able to do this within one loop for int x equal to 0 while x is less than size divided by 2x plus plus. I think if we do a at, we'll do unsigned. Unsigned char pointer temp is equal to a at x. And then a at x is now equal to a at x minus 31 minus x. There we go. And then a at 31 minus x is equal to temp. So this will just swap those 2 bytes. So what we're going to want to do is this on the public key. Reverse p underscore public key at, well, regular 32 bytes. We don't want to do 64 because we don't want to reverse x and y. That was still correct. We just want to reverse them at their location. So then plus 32 will get us the y coordinate to swap. Since they're all calling the same function within the function, so all call and copy, this is actually a reverse function. Reverse copy. We could step through it in GDB to confirm that, but I'm just going to tell you now it is. So we also need to reverse our private key. It doesn't matter so much now when our private key is all the same characters, but later if we change that, it become important. So private key, reverse that. GCC size divided by 2 doesn't work. What? Size isn't undeclared, it's right here. Oh, semicolon. Run that. We now have F5 as our first public key. That doesn't sound, oh, no, that should be our second one. So it's Y, F551, so that looks right. We can get rid of this print and close and check to see if this answer is now the same. If it's not, I'm going to pause the video and try and figure out what I'm doing wrong, because I think it should be. So that's before we step over, check it out, and see that it is indeed 19B0E091. So that's good for us in the sense that we were able to correctly identify it. It's also bad for us in the sense then that means this elliptical curve cryptography function is entirely correct. It's implemented safely, doesn't appear to be anything wrong. Your first identification might be the fact that private plus n might be interesting to look at. The fact that we're doing our private key plus n actually falls outside of the bounds of what should happen here. Because right here, our private key should be a randomly selected integer in the range of from 1 to n minus 1. And the fact that we're above that actually messes that up. But if you do the math, let me see if I can, let me open up a notepad and see if I can just mental out the math just with some basic algebra. If we do the math, it actually shouldn't matter. I think it's, I'm not sure what it's doing right now because we don't know what function it's doing, but I'll just do A. So usually a private key is a random value on the curve. Q, so let's say that's the private key. Q is our private key times G. That is the result of adding G to itself D times. So if we were going to find a shared secret, it would be, we'll say Q1 is D1 times that, and Q2 is D2 times G, so we'll have two people. Our shared secret in what our decryption key is going to be will be D1 times Q2 or D2 times Q1. But if we actually were to overwrite this as D1 is actually D1 plus N times Q2, it will break down into D1 times Q2 plus N times Q2, which can further break down into Q2 plus N times D2, put that parentheses, it's actually D2 plus G, so D1 times Q2 plus N times D2 plus N times G. N times G should just be, I think N times G, what is N times G? That one should be in here. N times D2 is not the same, but it's just brings us back to N times D1. Oh, that's N plus. That's not the same at all. N times D2 should actually just be, that is G. What is G? If I remember correctly, G is a point on N. So this actually just turns into G. And this would turn in, or maybe it's just the private key, and this just turns into G. Mostly turns into the fact that since this is still just, this point right here is still equivalent to G mod N, since it's still just going to be the point G on the curve N, it turns into nothing, so it's still fine. It more or less just adds values to it. I think it's normalizing the curve, but I'm not sure on that. But if you were to identify anything wrong, that'd probably be your first spot, because that's a function that's not normally in this implementation, or at least this implementation it's not. But more or less, it turns into nothing, so that's not even the point. So the fact that this ECC looks perfectly fine makes us think that it's not actually the implementation of ECC that's wrong. So let's go back to decrypt. This video is getting a little bit long again, so I might have to split up into another part. And I'm going to quickly identify what we need to do in the next part before going forward. So we had identified that this appears to be fine. So we're still missing HMAC data and private key. But what we need to notice is that to identify the HMAC, since this is Zord and then SHA-256, we need to identify what might be this data. Since it's a CTR cipher, CTR ciphers work by the fact that if you use the same encryption for both of them, they're actually just going to be Zors of each other. So since it's using the same counter, or since it'll probably use the same counter every time, since it's going to be using a shared key, we might be able to identify what this data is. I think in this video I'm going to identify what the data is, and then that'll help us identify what our target is. So with that, let's identify. So we know the data is going to be going through. We have currently, delete all this. We have a structure that's kind of made up of this. We have public key X, public key Y. Both are going to be 0x20 bytes. We have the checksum, which is 0x20 bytes. That's used down here from our socket buffer. And then we have the rest of the data that's whatever size. We know only 0x60 bytes are being used within this decrypt function. Go back to command thread. So we need to know what's being used with the rest of the bytes. Our packet that's being sent in is lstech data raw is 288 bytes. Off the top of my head, I don't know what that is in hex. Do hex of 288, 120. So that means after doing 60, we're left with 0x80 in bytes, I think. Nope. 0xC0 in bytes. So that should be 40, yeah. So there's 0x6 or C0 data left in our packet. We need to identify what's happening with that to help us better realize what's going on. We know that after it's decrypted, it's sent into this function here, which is probably going to be a command loop or like do command, just based on got command and then whatever string's inside. And this also has the switch statements. So we know our string is going to be one of these two. It's probably this one. I'm not sure what param1 is. This is probably our command string after it's decrypted. So this will be param2. We'll do command string. And it looks like just right away we're having the string be sent to string to long. So it's converting whatever's in here to a long. It has it on base 10, so that's good for us. We know it's going to be an integer. The first one's going to be there, then the next one's also 0x40 off. So we know the first bytes. Let's see, how do I want to do this? We're going to do a structure of some sort. Remaining. The first bytes, we don't know how long, so we're going to say 0 bytes to question mark. At most, it's 0x40 because that's going to be the next index. So 0x40 to question mark, we don't know where the next one is going to be a long. We know this one's also a long. Put those both to the same spot so it looks a bit nicer. And we could follow these down. So I'm going to just follow 9 first. Following 9, I'm not seeing it being used directly anywhere right away. Maybe I didn't. Oh, there we go. I didn't click it right. It's used right here. It's used within the switch as well. So it looks like this first value is going to be our command type. So if you remember, the switch case gave us some kind of function call here. So updated HMAC key. So it looks like one switch. We don't know what those ones are. We know this one sends data to the navigation service. And we know that this one started the SSH connection. So we know that this first possibly 40 bytes, maybe it's less, maybe it's more, is going to be our command type. Oh, it can't be more. So I'm actually going to rename this to command type. It looks like it needs to be between the range of 1 and command needs to be less than 6 actually. It needs to be less than 5. So there's only command type -1 needs to be between. Let's check this to see if it's a signed. It just says branch high, so that's an unsigned check. So it needs to be between 0 or 1. Normally 1 and 6, maybe 7. 1 and 7. If 6 is less, yeah, 1 and 7 on an unsigned check. So our command needs to be between 1 and 7. Those are the only values it could be. This next case, we're going to follow this value. var 9 needs to be less than 10. Is that an unsigned check as well? We can tell it's an unsigned check based on the branch high. Branch high is an unsigned check with an arm. So we know this one is going to be between, since it's not doing -0 and 10. We don't know what it is yet. We know it's going to be between 0 and 10 though. We could follow it down further. It's used as a return value here. It's used as a checks to see if it's 1 there. Checks to see if it's 1 there. Return value there gets overwritten here. Another return value doesn't appear to be used really anywhere else. It looks like the main one is this return value, which updated HMAC key. Not sure why that matters too much, or if it's checked to 1 here. Those looks like be the only two. We could also follow uvar6, see if that's used. Oh, uvar6 is used at more places than uvar9, so let's follow that one instead. So it looks like in case 2, I'm going to set a little. So in command 2, this needs to equal 1. If it doesn't, it fails. In command 3, this needs to equal 2. In command 4, it needs to equal 2, so I'll do 3 and 4. In command 5, it needs to equal 3. If it's not, it doesn't. Command 7, it needs to equal 3. It's not used in the other command. This last switch down here, we should probably identify that since it's not being directly identified for us. I think if I do this and go back, looks like it's case 1. So case 1 will be the SSH. That might not be a bad thing to label. So commands so far, 1 is SSH stuff that we already know what it does, so we don't need to worry about anymore. Case 2 looks like it's an update HMAC key. Update HMAC key. Case 3. We're not sure what it does. It looks like it's grabbing a value, setting something in memory right here. So we're not sure. Set memory. Question mark. Case 4 looks to be zeroing out this memory. So this one is turning something on or turning it off. This is doing the opposite. Set memory. We'll do inverse of 3. Case 5. Sends to navigation. We can figure that out just based on this string that it's talking about the navigation service. So far we haven't used that because we don't have a navigation binary. We don't know what's going on with that. Case 6 sets this memory address to 0 just straight up. Doesn't need any parameters or whatever we think this one is. Hence, there's a good chance this might be the number of parameters. So that just sets memory to 0. Case 7. Case 7's a little bit more complicated. Looks like it's setting some values to 0 as well, or setting some values in memory as well. It's at param1, so we could follow it, see what param1 is at 38, 40, 48. It also frees the data if S is not 0. Not sure where S is set. S is set to command stream plus 80, so we're going to have to follow that one. That's actually good to know up here. So 0x80 to question mark is a character pointer possibly. Looks like a stir dupe, so yeah. So this appears to be using that as a character pointer. We don't know the length yet. There's a good chance that this one is going to be then going to 0x80, and then that kind of reaffirms our hypothesis right here that that's 0x80 as well. Tab that one in. If it's been 0x40 here, there's a good chance it's continuously going to be 0x40, so this is maybe 0xC0. All we know right now is it's a character pointer. We don't know what's there. Command string at 0xC0, so it lines up with that. It also goes to 0x100, so we could just copy this line twice. 0x2, 0x100, 0x100 to probably 0x140, but we don't really know. It's doing another string dupe, just checking to see if that's a null byte. If it does string dupe, it sets it to memory. So it looks like we're setting something in memory to these values that would be in here. We're not sure what these pointers are, but they look important. With that said, we know that our data coming in isn't going to be K7 because we're not working with 0x 140 bytes. We have 0x C0 bytes. So we need to find one that narrows down with that more. So case 7 sets strings in memory, or copies, I guess I should say, not sets. Copies strings in memory. The length of this one is 0x 140-ish. Case 0 or 60, or not 60, C, doesn't use any parameters, doesn't use any values. So we're not really sure what the length is here. This could be anywhere between 0 bytes to 140 so far we've seen. Case 5, so a couple of functions. Does a string length. Case 5 was the navigation one. It looks like param1 at 1A0. I'm not sure param1 is, so let's go back. Not really. I don't like Ghidra too much when it jumps into the switch case for me. It makes it easier sometimes, but you also lose sight of what the parameters are. So it looks like case 5 is using 0x100, and it's also using 0xC0, so there's at least 140 in 5 as well. 140, put parentheses around that. So this kind of, it takes a little bit of guessing, but this helps narrow down that this actually stands for the amount of arguments. So 0, 1, 2, 3, no, that's the commands, 1, 2, 3. So these would be the parameters length, or parameters. And we know 5 and 7 are using at least 100, so they needed parameters to length 3. 6 we don't know. We know 3 and 4 need 2, so there's a good chance that they'll need 100 bytes. We can check that out, 3 and 4. Command string at 0xC0, so it's going to take at least 100 bytes. So that's correct assumption there. So it's 0x100 in length. Is 0x100 in length. Case 2, it says it only uses one parameter, is what we're lining up with. So this could be 0xC0. Whoops, didn't mean to close that. If we follow S, S is just the command string at 0x80, and it only uses S, so that lines up. So it only uses this first parameter. SSH, which would be case 1, doesn't appear to be using any parameters. I'm not seeing any checks, so we're not sure what this one could be. This one could also be between 0 and 140. But since we know how much data we actually have, our remaining data is 0xC0. There's only one that actually directly fits that. So there's a good chance that the packet coming in is going to be an updated HMAC packet. The reason this is useful is the fact that there's a good chance now we can guess what the packet looks like. We know that the command type needs to be command 2. So our packet most likely is the number 2, then probably followed by 0x00 times 0x3f. This is just an assumption, but you kind of need to start making assumptions when you're running out of data or paths. So we know the command type is 2. Then we also know that the parameters is what we think this is. Parameters is going to be 1 plus 00 times 0x3f. Don't need that one there. So now we just figured out 0x80 bytes of our 0xC0. We don't know what the HMAC is being set to, but it being 0x40 bytes lines up with our previous activities that we had seen with it opening HMACs as opening the HMACs as just 0x40 bytes at max. So this kind of lines up with what we're working with. I think that's actually a good spot for us to stop. This video had gone on a little bit longer than I was hoping, mostly because we were trying to get the ECC working, and we got it. But now that we have identified what the packet looks like, there's a good chance that we're able to finally decrypt the packet at the end. So with that, I'm going to stop here, and then in the next video, it should be the last video within this task 8. Thanks for watching.